Assalamualaikum and good day. I am one of NABILA BINTI ADLI with my friend Tineswar, AHMAD, SYAHMI, and also NAVEN. We are from Group 11. We will explain about Laboratory 1, which is heat transfer conduction. For the introduction, heat defined as energy that flow from one body to other body due to temperature difference, which is flow from high temperature to lower temperature. Heat transfer conduction defined as one of the basic thermal energy that transport usually used in all heat transfer process. This figure shows one-dimensional heat transfer conduction example. Below, we show the one-dimensional heat transfer conduction formula, which is integrated from the Fourier's law. In this experiment, we have three main objectives, which is to perform experimental investigation of linear thermal conductivity of brass and also stainless steel. Next, perform experimental investigation of radial thermal conductivity of brass. Lastly, to calculate the rate of heat transfer from linear conduction through cylinder wall. The theory of this experiment is actually, in this experiment, a heat conduction study bench was used. The experiment conduct with different range of voltage supply, which is from 5 until 20 watt. By using two different materials, which is brass and stainless steel, the linear module used to investigate about linear heat conduction by help of 7 thermocouples that attach at the linear module to have a different value of the temperature at 7 sections. The temperature is different to manipulate the flow of heat conduction in cylindrical section. The temperature setup is the same for radial module. Both of the experimental results were recorded in table respectively. For the apparatus and setup, we actually use stainless steel, brass, heat sink base, water supply, power regulation, linear module, and radical module. As you can see, the figure actually shows our full setup for the experiment, which is for linear module and also radial module. In this experiment, for linear and radial, we actually use the same procedure, which is we have 8 main steps, which is start with all material will prepared, and then the heat sink paste applied on the surface of the material. After that, the water supply will turn on for the heat sink. Meanwhile, the power regulation will turn on in order to preheat the heat sink. The power regulation then will adjust into several desired voltage, either 5 until 20 watt. Before we use the system, we actually wait until 5 to 10 minutes to make sure the system is steady state. The temperature measured for the experiment were recorded in data system. And then lastly, the experiment will repeat into several different types of material and voltage in order to get another data.
Hello, my name is NAVEN SANKRAN and my metric ID is MA19275. So now I'd like to explain about the result and data of our experiment. So first is this is the data given by our lecturer. So now first is a linear module. We used stainless steel and the diameter is 25 mm. And first column, the first table is 5 watt of power. And then the second table is 10 watt. And the third one is the power 15 watt stainless steel as before. And this all tables are include of location, temperature sensor, and then the temperature. Next is for the linear module, but this time it's about the brass. The same diameter as 25 mm, and the power is for 5 watt. Next, this is about the radial module, and the material we use is brass, and the diameter is 110 mm, and the power we use for 10 watt and 20 watt, and these are the data we have given from our lecturers. So now I'd like to explain about the discussion. Our first question is to plot the temperature profile for each heated power value for the linear module. So our graph will be like temperature versus the location. So and we include 3 datas in one graph, which is for 5 watt, 10 watt, and 25 watt for stainless steel. And next will be like brass. There is only one data which for 5 watt. So second question is to plot the temperature profile for each heater power value for the radial module. Radial module, the given data was 2, which is 10 watt and 20 watt for brass. So that's all from me. Thank you.
Hello everyone, my name is Tineswar, son of Jaganathapillai. My metric number is MA19217. and I'm here to discuss about the calculation of thermal conductivity for both type of experiment, which is linear experiment and then the radial module experiment. So let's look on into the calculation of thermal conductivity for the values of each linear experiment and also the radial module. Okay, let's see how the calculation for the thermal conductivity. In order to find the thermal conductivity, we need to find the temperature gradient first before we do the calculation for the thermal conductivity. So for the calculation of the temperature gradient, the formula is dT over dx, which is the highest temperature minus the lowest temperature in the data given. And then same goes the location, highest point minus by the lowest point. So after subbing the values into the formula, we could get the temperature gradient, which is 96.5 Celsius per meter for the stainless steel material for the power of 5 watt. So next we move on into the thermal conductivity calculation. We need to do the calculation to find the thermal conductivity by using the thermal conductivity formula. Thermal conductivity formula is which is Q equals to K thermal conductivity and times by A, area of the material, and the time, and then times with the gradient, temperature gradient. So material we use is the round circular type, so we use the A equals to pi r square formula. Okay, after subbing all the values that we have in the experiment, so finally we would get the thermal conductivity of the stainless steel material, which is 105.55 watt per meter Celsius. So the calculation we need to repeat for the each of the material, each of the data given in the lab sheet. So in order to get the thermal conductivity, so here we have the material stainless steel and also the brass. So the only the power is varies for each of the experiment. First is 5 watt, 10 watt, and then 20 watt. So same goes to brass. We only have brass one type, which is 20 watt. Okay, next is the radial module experiment. Let's we see how the calculation of thermal conductivity values for each of the radial experiment. In the radial module experiment, the way of find thermal conductivity is different a bit. Means the formula is different a bit. Firstly, we need to find the thickness of the plate by apply the data given in the lab sheet. So the thickness of the plate is 0.03 meter, and then the R2 is 0.02, and then R9 is 0.07. So the formula is Q equals to 2 pi L thickness K thermal conductivity bracket T1 minus T0 divide by ln the R0 over R7. So the Ti is represent the temperature of T2, whereas the outer temperature represents T0 represents the temperature at the point T7. So after we find the temperature points, then need to find the thermal conductivity by the formula for the radial module experiment. So after we apply all the data given in the lab sheet, we would get the thermal conductivity for the power of Q 10 watt, which is 20.6 watt per meter Celsius, and then for the power of 20 watt, we can get the thermal conductivity, which is 21.90 watt per meter Celsius. So the power increases, the thermal conductivity also increases slightly. Okay, next we move on into the discussion number 4, which is the comparison of the calculated thermal conductivity to its typical value, and then the explanation of the discrepancy in the data. So based on above calculation, stainless steel has a higher thermal conductivity thus in the power inputs and the linear conduction experiment. So here we see 5 watt, both is 5 watt, and the specimen we use is 25 mm brass and then 25 mm stainless steel. So we get the stainless steel, which is higher thermal conductivity based on our experiment, whereas the brass, which is 92.70 watt per meter Celsius. It's because of the various temperature and element composition which can impact the rate of conduction. Theoretically, brass must have a higher conductivity than steel, but based upon our calculation, stainless steel has a higher conductivity than the brass due to the power inputs. All readings were recorded twice to obtain the average temperature. The average temperature will be recorded to reduce the errors. Finally, the thermal conductivity of the material is inversely proportional to the temperature gradient according to Fourier's law. As a conclusion, the higher the temperature, the decrease between the two connected elements of the same dimension to hot or cold reservoirs to a lower thermal conductivity. When comparing two materials, increase to power output is larger, they generate more heat conducted along the composite bar, contributing higher temperature difference. So as a conclusion, based on the calculation, we have the stainless steel as a higher thermal conductivity than the brass in both power inputs in the linear conduction experiment. Thank you. That's all about my part.
Assalamualaikum warahmatullahi wabarakatuh. My name is AHMAD bin JAMLI, MA 19036, and I will be presenting on discussion and conclusion for heat conduction heat transfer lab 1. For discussion number 5, the heat conduction in this experiment requires cooling water flow. What do you think is the reason behind this? Cooling water flow is needed to maintain the overall temperature of the sample. The flow of electricity will release heat energy due to resistance. The fluctuation of temperature of the sample will cause the data to be inaccurate and unable to perform analysis. For question number 6, state 3 reasons why the thermal conductivity value for a particular material is important in engineering. First, to determine the right material for heat insulation. Second one is to determine the right material for heat conduction. And the third one is to describe how well the heat energy flow. For question number 7, give 3 examples of heat insulation method used in engineering nowadays. First one is blanket insulation, insulation board, and loose fill insulation. For the conclusion, the objective of the experiment is to achieve where linear conduction of heat transfer along the homogeneous bar is well investigated using Fourier's law. Theoretically, brass has a higher thermal conductivity compared to stainless steel. This therefore allows heat to travel efficiently through brass compared to stainless steel. But for our experiment value that we had found, stainless steel has the value of 105.55, whereas brass has only a conductivity of 92.70 watt per. Furthermore, the gross tabular data confirms the theory of heat conduction, which states the energy is transferred from more energetic particles of a substance to a nearby less energetic particles as a result of particle interactions. When a temperature drops with increasing distance, heat is carried in the direction of falling temperature and the temperature gradient is negative. That's all from me. Thank you.